Determine the shear and moment in the beam as a function of x. To begin, we're going to start with converting our uniform distributed load into our point load. So this is going to be 0.5 times 200 times 10 feet, which comes up to 1,000 pounds. And then at B, we're going to have horizontal, vertical, and moment. Horizontal will be 0 for B, because no other force is acting on it. And By we have to still calculate. To calculate for By, all we have to do is sum the moment in y direction, and we should have our solution for By. So we're going to have 800 pounds negative 1,000 pounds, positive By, all equals to 0. For By, we have our solution as 1,800 pounds as a solution. Now to find the function of x for shear and moment, we first of all have to convert our triangle load into load equation, and we'll use proportionality for that. And we know we're going to have 200 pound distributed load at 10 feet, and we can have 0 load at 0 feet. Starting from the left hand side, simplifying this equation for our load, we're going to have our solution as negative 20x, and this is going to be in pound per foot. Now we can take the integral of this load equation to find our shear equation as a function of x. So we're going to have negative 20x squared divided by 2 plus our constant. We can simplify this, and it becomes negative 10x squared for our quadratic equations here. So, and to find the value for our constant, we know our shear is going to be negative 800 pounds when x is 0. This tells us our constant is negative 800, which we just simply have to plug into our shear equation to have it completed. Similarly, we can have another integral to find our moment equation, but this time the integral will be for our shear equation. So this is going to be negative 10x cubed divided by 3, take away 800x plus our constant. And to find a constant for this, we know our moment is going to be counterclockwise 1,200 pounds foot, and our x in this case is 0. Therefore, c is equal to negative 1,200. We're going to plug that into our moment equation. We're going to have negative 10 divided by 3x cubed, take away 800x, take away 1,200. Determine the shear and moment throughout the beam as a function of x. To solve this, first we're going to convert our distributed load into point load. In this case, it's going to be 2k times 6, which is 12k. And this is going to be 3 feet away from our initial point, which I'm going to name it A. And since this beam is embedded into the wall, we can have a regular external reaction forces, which is horizontal and vertical. Horizontal is going to be 0, and then we're also going to have a moment, this point. Alright, now let's find our value for AY, which is very simple in this case. Just have to sum the forces in y direction. We're going to have negative 12k, negative 10k, negative 8k plus our AY, all equals to 0. Solving for AY, we're going to have our solution as 30k positive. Now that we have that, and to find our functions, first of all, we have to recognize that there's going to be two regions for this beam where changes in load are occurring. We're going to have one region which is 0 to 6, and then another one is from 6 to 10. For region 1, first of all, we need our load equation, which in this case is super simple. It's simply -2. Now we just take the integral of this load equation, find our shear equation. So this is going to be -2x plus rc. And we know our shear is going to be positive 30 when x is 0. Therefore, c is 30. We're going to plug that back into our equation. And to find the moment, we have to again take the integral of our shear. In this case, it's going to be negative x squared plus 30x plus the constant. But before we proceed to solve for our constant, first of all, we need to determine our moment A here, which we can find by taking the moment about the point A. So we're going to have sum of moments at A, counterclockwise as a positive, so we can have negative moment A, and then clockwise we have 12k times 3 feet, then we have clockwise 10k times 6 feet, and then clockwise 8k, and it's 10 feet away, and finally our given moment, which is clockwise 40k feet, all equals to 0. So for moment k, we get moment A, we're going to have our solution as negative 216k feet. This negative simply means that this moment is counterclockwise. All right, so now we know that our moment is going to be negative 216 when our x is 0. This way, we get our value of c as negative 216. Okay, now that we have all the required equations for region 1, we can proceed to region 2. For region 2, we don't really have any load equation. We can say it's 0. And to find our shear for this region, we first of all have to know that if we take the integral of the 0, we're just going to have our constant. And now to find the value of this constant, all we have to do is just take the shear equation from region 1, which is -2x, and we know that this region begins at 6 plus 30, and then we have to look for any other external reaction force at this point, and that we know that there's going to be -10 external reaction force, all equals to our constant. And solving for this, we get our solution for C as positive 8, which is also our shear equation. Simple constant 8. And now to find our moment, all we have to do is take the integral of the shear. So we can have 8x plus the constant. And we know our moment is -40 when our x is 10. And so for this, we get our constant as -120. And this gives us our equation to be